Hello, this is my English speaking practice, and I'm talking about my yeah my training of coding, right? And yeah, I'm working on lead code, and right now I focus on dynamic programming. I yeah, but I I feel like I I solved a lot for dynamic programming. So let me filter out. So this is the problems, and I've already solved 53 problems. So from today, I solve problems randomly, so I don't know what kind of the problem. Okay, yeah, it's close to the real tech interview. Okay, so let's go. Recover binary search tree. You are given the root of a binary search tree where the values of exactly two nodes of the tree were swapped by mistake. Recover the tree without changing its structure. Okay. So in this case, the root node is 3 and it have 1 as a right child, but it's not valid because binary search tree should have larger one as a right child. So the answer is like this. And how about this? 1342. This part is good. This part is good, but for this is not good because it should be like this. Okay, but I think that there is another answer. The 2 is connected to 1 because 2 is right side on left side on 3 and right side on 1. Okay, so I think there are 2 answers. 2 cannot be in the right side because 2 swapping and the right. Yeah. Go on the tree without changing its structure. Yeah. The program doesn't mention about it, but I think there are multiple answers, valid answers. Okay, and follow-up question. A solution using OON space is pretty straightforward. Could you devise a constant O of space solution? Okay, I see. Constant space. Anyway, let's create a file. October 9th. Recover binary search tree. Do not return anything, modify root in place instead. Okay, I see. And let me think about the straightforward solution. Hmm. Yeah, it seems apparently we can do it with O of n space. Okay. Straightforward. Hmm. Yeah. Yeah. I see. I see. Maybe we will do DFS and DFS and store the node value. Yeah, and to compare the node value with the node value we already met, and but DFS, let me write a code DFS, and it take node, it takes a node, and yeah, when we DFS, this function should be recursive, so it calls left side and right side. Like this, and DFS, and for this path we are expecting the node value would be smaller. Yeah. So maybe this function takes parents, and this is a set. How to specify the set? Yeah. Yep. And like this, append the node value to the parent set, and oh wait, but in this function yeah, in this function we don't know what which is which is expected, greater than or less than. Okay. So let me write BFS 3142. Hmm. Upper bound and lower bound are we can how about this? So for left, for left, okay. So lower doesn't change. Any, yeah, lower, whatever is good. The upper, for upper, not value, and vice versa. And okay, so we have we get range, valid range. So lower node value. Oh, this is good. This is valid. So we continue to search further. Otherwise, it's invalid. Yep. Okay. Okay. Yeah. We need to swap the node. So swap the node value. So the node value less than lower. It's invalid. So node lower and maybe we have to return something. We have to return temporal. This case, lower is 4. 4 is good. 2 is not good. Huh? Okay. I think this is not good. Let me see. Let me see. 3, 4, 3. One is good. Return 4. 2. 2 is not good. So this would be exactly 2 nodes of the tree swapped. Okay, so we have to find one pair, and yep, we can find this way. But how do I swap it? $23. Lower is 23. Yep. And here upper is 23. Lower is 23. So yeah, 2 is not good. Else. don't know. Four left. Four left. Four left. I see. I see. I see. In this case, if node what should I return here? What should I return here? Yeah, if we find the invalid value, we can return it, and it take it. Okay. Can I return null and we don't do anything? If it's not none, we have to use it, swap it, right? No. This return 2, okay, and here we don't know. We should swap that value or not. Okay, cause in this at here the lower bound is 23 and return 2. That's not good. Okay, we can, yeah, we can use the lower bound. If lower it means yeah, lower if it equals to node value, it means the invalid node at the time. So we can use let in this case. Oh, it's opposite. Upper node value let. I think so. So when we call next function for left side, the oh yeah, upper, oh, wait, I'm confused. 23 and negative infinity and positive infinity, and 23 is good, so we call for left and for right. And for right, we can specify 23 as a lower bound, and this calls this is called recursively. And next is 54, so the lower but the range is 23 and upper is 54. Great, 54, and it reaches 2. Yeah, 2 is less than the lower bound, so we return the 2. Okay, and the node value would be 23. Okay, return 2, and return 2. Okay. This case, we should return red. In this case, we return now because we have already done the swap. This is also same. That's it. Yep. Lower and upper. I'm not sure, but this works. I'm not sure. Wrong answer. Okay. One, 3, 3. Okay. Root node cannot be replaced. Cause it should be node bar. Ah, I see. Mm. Return it. Return it. No way, no way, no way. Node bar. Oh. Huh? So. Okay. I think we need the value should be replaced, and so the target if it's same, we should replace it. Okay. Yeah, I think so. Does this work? Cannot unpack non-returnable. Ah, I see. So the whatever it should return okay, but I'm not sure. I'm not sure, but the number of nodes in the tree is in range to 1000, so 1000. Okay. Let me submit. Wrong answer. Okay. I know. 231. Oh, it renders 231. 231. Oh, I see. 2 3 1. Two, three, one. So we should swap 3 and 1. But we cannot swap anything. Yeah, in the current implementation. So how? I think we traverse tree from smaller, and if we find the smaller, if we find the smaller value than the values we already have, we swap it. Just swap it. Small. Oh, this is not good. So we should swap the. But how do I identify the value that should be replaced? So we have numbers. We have numbers in ascending order, and in this case -1 and 23, and we find a 2. Which one we should replace it? I think we cannot solve with one DFS because it feels like difficult to go back to a proper node. Wait. And maybe count. It takes count. It is like an index, and we should work trees from smaller, so return if no work from smaller and node left. Okay. And count no, we just have upper bound and cause we work from smaller side, upper should be updated here, but we should check if upper is less than node value. This is in normal case. Upper should be updated here, but yeah, we reach here once. It should be replaced. Yeah, but I don't know how should we do here? And smaller node, right? Okay, and return. Upper is updated. The node value should be replaced. So if we find the node value, we can return it. And we don't need to work anymore. So we can get value to be replaced from smaller and root, and upper is should start from lower minimum value. Yeah. And workforce swap. Target value. It takes target value and workforce swap. So the value, yeah. And if it's yeah. Just return if we have to work for swap. For left and if target is, yeah, should be replaced. Should be replaced and no, node value, be replaced target, and we need to replace one more time. The node where the target value is originally placed. Okay. Mm. So we have to replace twice. So how about flag? Replace first, replace second. If it's not first, if it's second time, we have we have to the value the value would be we have TZT1 and TZT2. So this is TZT1 and we call workforce swap. TZT1, TZT2. TZT2 is temp. Right, its first is false. TZT1 would be the value to be replaced, so we can find TZT1. We can find a node by comparing TZT1 and node value because it would be same and it's a node to be replaced by target 2. So node value would be TZT2, right? Oh wait. Right? this case, TZ, T1, TZ, T2. Yep. Root target 1, target 2 is whatever is first is true. Missing required potential argument. Upper. Oh. Upper is updated. How about this? 3 required potential arguments. Why the language server doesn't no. Hmm? Three, two, one. 3, 2, 1. Why? Work on smaller and we work for left. 1, 3, 2. One, 3, 2. 3, 2, 1. Yes, 3, 2, 1. 3, 2, 1, 3, 2, 1. Hmm? 3, 2, 1. So, oh, I see. Oh, this is not good. 3, 2, 1. 1, 3, 2. So we find 3 and then we find 2. This at the time 2 is less than 3, so we find that's not good, so it returns 2 as a value to be replaced. But it's not correct because we should replace 1 and 3, right? Oh, so this program is wrong. Okay, I see. But we have to handle this case. Two, three, one. 2, 3, 1. This case we find 3, 2. Okay. Okay. Maybe maybe we should find the maximum value of the left side and the minimum value of the right side, and we compare them. How do I swap it? That's a problem. Three, nothing. 3, nothing. But 3 is greater than 1, so it's not good. We should replace it. And But this case is easy. We can find 3 and 1 is wrong. They should be replaced. How about this case? Find 3. This is 1. Not good. 3. I'm not sure, but DFS, I don't know, and it's optional 3 node, and that's max left DFS. So the DFS function should be yeah. How about this? If this is the case, lower upper should be replaced. So replace old and new. Old, new. If node tree node, okay, and return it. Node and node dot bar equal old. We can replace it. So node bar would be new. New. Yep. Return. Otherwise, replace call replace function. Old, new, node left, node right. This is not efficient, but I have no idea. This case, replace old old is old is upper lower. This is the left side, okay, cause oh no, lower upper, right? If lower is less than upper, that should be, this value should be left side, should be moved to the left side. So the old one is upper value and new one is lower value. Yeah, it must be in the left side in the node, and vice versa. Lower should be replaced, right? And for the another case, else if node value is less than the left one, upper one, yeah, replace old one is upper, new one is node value, node left, okay, and after the node value would be upper, yeah, correct. Else if node value yeah, lower is less than node value, yeah, it also should be replaced. The old one is lower value, new one node value, it must be in node right side, and node value would be left lower value that is originally in right side, and otherwise that is valid so far, so we just we have to return the upper value and right, upper and lower. Yeah, so the value would be upper, if it's upper, return upper. And so after replaced, we have the binary search tree is already swapped. So if it's upper, we should node value. no. This case, lower, upper. This case, left side. In this case, left side is replaced already. Right, left, right, left, right. No, 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 no. What? Left side upper and right side lower. Hmm? Mm. DFS, DFS. Going to right. Here is a base case. Else going to left. Is this correct? We have I have no idea. I don't know. I'm not sure. Okay. But what should we return? No, this no. What? 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 Searching. Oh, it's good. Okay, return it. Searching. Oh, it's not good. Let's swap. That's all, right? That's all. We can return it. Okay. Searching. It's good. Nothing to do. Okay, we can return it. Yeah. But we need to search. Search. But it might be replace. Might replace something. DFS. This function return the upper bound or lower bound, and also might replace. Okay. And we have to find upper bound and lower bound. How do we do that? Like this. That's good. This is good. If it's upper and if if there is right node, if the node have right node, we can going to right side, right to right to right to right. Okay, that's the upper bounds. Okay, this is a lower bound. Okay, this is good. This is good. This is good. But we have to care. We have to care about node is none. The only one solution is like this. And upper is yep. Upper should be left side, upper bound of left side, but there is no left side node. Node on the left side, we return the node itself. And likewise, the node doesn't have a right node. Return the node value as a lower bound of the right side. Okay, so this might be node itself. So we have to update this part because it might be node itself. So we just compare lower and upper, and if it's reversed, so in this case left side and right side, we can this. So node bar should be lower, and right. Left, right, and if it's reversed and the node value same as the right side, node value is right side, but left is, yep, left is bigger than the node value. The node value is left, and we have to replace the left side. The old value is left, and new value is node value. It's right. Yeah. Else if node value is left, node value should be right, and replace old is right, should be left, node not right side, and else, yeah, it doesn't contain node itself, replace old is left, new value is right. We replace the left tree, and old is right, new is left, and it replaces right tree. That's all. That's all. DFS root is upper. Oh wait. Whatever. Anything is fine, I think. I'm not good at binary search tree. Wrong answer. Oh my god. Oh my gosh. 3, 2, 1. 1, 3, 2. 1, 3, 2. 3, 2, 1. 3, 2, 1. Why? Two, 3, and 1, 3. I gave up. Solution. Let me see solution. In order. Going in order. Self-priv value is greater than node value, and okay, we prepare three global pointer. First, second, priv. And if priv is and priv value is greater than that node value, and if not first, we store the priv value as a first, and the second is this. Second is like this. First, second. So we should find first and second. And previous is used for tracking. Okay. So yeah, priv this is updated in ascending order because this is in order traversal, and priv val is greater than the node. Okay, so this would be I think this would happen once or twice. I don't know, once or twice. Priv value is greater than node value, and if it's first time, we update first. Yeah, to keep track of the first. Priv is always be updated. Priv is always updated. Okay, and if it's first time, first is updated, and second time, okay. So I guess this condition meets twice in this problem. In order traversal produces a solid sequence. If two nodes are swapped by mistake, the order traversal will show a violation of the increasing order. We can detect these two nodes during in order traversal and swap their value back to fix the BST. In previous mistrans, violation occurs. there can be one or two violations depending on whether the swapped nodes are adjacent or not. After identifying both nodes, simply swap their values. Once or twice. Once or twice. Okay. Let's see. If they are adjacent, it's occur once. If not adjacent, that's a edge case. This is the edge case because it's adjacent. Adjacent. So we find 3 at first and we find 2. Oh, that's not good. So at the time, first is 3 and second is 2, but after that we find 1, so 1 is also not good, so we can update. The first is 3 and second is updated to 1, so finally we can find 1 and 3. Yeah, right? Okay, I understand. So but I don't know, I cannot explain it why this is right. So the key thing here is first pointer should be updated at once, because the first appearance, the appearance of the violation, okay, so that should be updated. The first violation. The first violation, so it's greater value, and at the same time the second one is less than the first one, but the second node might be updated later. Yep. Like this. 3 2 2 1. Oh, in this case it also have two violations. So the traversal is 3 2 1. Yeah, 3 2 1. Oh, that's same, but the structure is not the same, yeah, and we have to handle both of them. 3 2 1, 3 2 1. Yeah. So we find the first violation, 3 and 2. The first would be 3. Second is 2. And we find the second violation. So the flip value 2 is greater than 1. So we update the second to the smaller one. Makes sense. So I have to explain it to show my understandings. Okay, let me, but this is not good. We have a more large examples. But it's okay. How about this? 1 and 2. This is not good. Invalid example, because we have to replace twice. So this example is not valid. This is good example. So we have 3 examples, and we are going to traverse in order. In order means going left first, and then look at a node, and then going right. With in order traversal, we can get numbers in ascending order. In binary search tree, because the left side should be smaller than the node, and the right side should be greater than the node. So basically, in order traversal gives us in ascending order arrays, right? But in this problem we have one mistake here. So the order is reversed. order is reversed. So we have to find it. So yeah, to find it, we keep track of previous node value. Yeah, previous node value. Yeah. So in this case we find 3 at first, and then we find 2. The previous is 3, so that's not good. It's descending order, so that's, yeah, we have to swap something, yeah, related with this. At this point, 3 must be replaced later, but 2 is not sure. Yeah, because if we find the number less than the 2, then yeah, it should be replaced. So 3, 2, and we find 1. Okay, oh, this is also not good. Yeah, so we have to replace something, and 1 is smaller than 2, so should be replaced. Okay, because yeah, the swap happens once, so the smaller one should be replaced. Okay, and also I don't know, let me more big example. Oh, I see. How about this? 9, 12. Oh, this is invalid. I don't understand it. So there must be two invalid placement. How about 4? Good. Oh, not good. It should be replaced. Good. But it's not valid. This is not valid as a problem. Okay. There must be two invalid, two violations. One violation, so two invalid numbers. Okay. So yeah. So I have to come up with the valid test cases, right? So first of all, we have to think about a valid binary search tree like this. For example, 12 and example 3 and 8 and like this. Okay, and swap once. 12, 8. Okay, so let's solve this problem. We work through in order. So 3, 5, 12, 10. Oh, it's not good. So the 12 must be replaced later. Okay, and 10, 8. Oh, this is not good. So we can identify two numbers to be replaced. 8 is less than the 10, so 8 should be replaced and 12 should be replaced. We could identify two numbers to be replaced. That's all. Okay. So that's good. But how about 8? One more test. Like this. 20 and 8. Okay, let's go. Let's walk in order. 3, 5, 20, 10. Oh, it's not good. 20 is bigger than 10. 20 must be replaced. And 10 might be replaced. Okay, and go to 12. 12 is good. 14, 14 is good. 15, 15 is good. 15, 8. Oh, 8 is not good. 8 is less than 15, so 8 must be replaced. So we can find two numbers to be replaced, 20 and 8. Yeah, because after we find the first violation, the remaining might be a valid order, but sometimes invalid. Okay, we got it. Yeah, I got it. Yeah, and when we find the first violation, that might be a pair to be replaced. But after for remaining part, they should be in ascending order, but there might be one violation because we the program swap once by mistake, so the remaining part might contain one violation like this. So we might find two violations for entire tree. So the first violation, bigger one of the first violation must be replaced, and the smaller one of the second violation must be replaced. So we can identify the two numbers to swap. That makes sense. Yeah, for remaining part, we must identify the smaller element in order to fix the mistake. Yeah. 10 is the first option. And basically it increases in order, but yeah, it might be another violation. Okay, I understand. And I'm not familiar. Okay, I'm not familiar with English phrases about binary search trees, so I will write a comment in English. Yeah, recover tree. Recover tree. Yeah, we traverse the tree. We traverse the tree in order, which expects that the number appears in order. Yeah. But there must be must be all the violations once or twice, because the one swap happened in the one swap happened in the original valid binary search tree. Does it make sense? Does this make sense? The one swap happened in the original valid binary search tree. So in order work, it takes node, optional tree node, right? And we have 3 pointers here to keep track of the tree node. Yep. Okay, and if node is none, we do nothing, so return it, and we call in order for left. This is the in order walk tree, and then we should compare the self node might be greater than the node value, right? That's a violation. So we keep track of those numbers, those values in the violations. So yeah, if it's for the first time, we have to update the first pointer like this, and the prev value self.prev value prev, yeah. Okay, because it must be replaced, because that's the bigger one. Yeah, and second pointer, second pointer, this, the node value is the, might be in the violations, but this would be updated because it's difficult to explain in verbal, but there must be 1 or 2 violations. So the In the second violations, the second pointer would be updated to node value, because the node value is the smaller one. So yeah, that is the final answer. Yeah, that would be replaced. That would be swapped. Yeah, because I see. It's difficult to explain this, but the one swap happened. So yeah, if second violation happens, the node value is the smallest value, must be smallest value. So the node value node, right? I think so. No. First, second. I think we should use value. Yeah. And after that, in order node right, in order root, and finally we swap the first and second would be pointer, should be pointer, and the swap is like this. Is this correct? I think so. We have 3 pointers to keep track of 3 nodes. Yep. First and second would be swapped. And leave is used for checking the order, right? In order function, walking tree in order. Here we go to left first. They they are supposed to be smaller. And we check the order here. If we find the violation, we store the node, and the first node, the first won't change. The first must be fixed because the first must be fixed because it's how do I say, it's it must be replaced. Finally, must be replaced finally. I'm not sure. And second one, the second might be updated. Yeah, second might be updated because the might contain another violation. Yep. Cause one swap happened. Yeah. Any two nodes. Random two nodes in original VS tree are chosen and swapped. I mean, hmm. Hmm. How about this? What? 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 Hmm. Oh. I I didn't know that this syntax. No attribute var. Really? Oh. Oh, we didn't. So the prevar would be great. Let's go. Okay. And the main goal is to learn English. So we traverse the tree in order, which means the node values should appear in ascending order. But since two nodes have been swapped by mistake, we'll find one or two places where the order is broken. To fix it, we'll keep track of 3 pointers. First and second are the two nodes that need to be swapped back, and prev is used to checking the current order as we traverse. We'll do an in-order traversal. First go left, Those nodes are supposed to have smaller values. Check if the current node violates the VST order. The first violation points to the first node to fix. The second one might get updated if we find another violation later, because any two random nodes could have been swapped. Move the play pointer forward, then go right. Those nodes are supposed to have larger values. After traversal, swap the two nodes values to recover the tree. Yeah. I have a lot suggestions. So I have to learn specific phrases that is used for when we talk about binary search trees. For example, toolbars and in order and appear in ascending order, or order is broken, and used to check the current order as we traverse. Go left. Those nodes are supposed to have smaller values. Violates the VST order. The first violation points to the first node to fix. Yeah. Okay. Since two nodes have been swapped by mistake, we'll find one or two places where the order is broken. We'll keep track of 3 pointers. And prev is used to check the current order as we traverse. We will do an in order traversal. Do a traversal. Do a in order, post order. In order and post order and pre-order. Okay. And we go to left first. First go left. Supposed to have smaller values. Second one might get updated if we find another violation later. Finally, we swap the value. Traversal, swap the two values, node values. Replace we and use present continuous. We'll go left. Have to check here when possible. Okay. Can I go next? Oh, binary tree. There is binary tree zone. Binary tree. Pass some binary tree. Okay, anyway. Binary tree zigzag level order traversal. Given the root of binary tree, return the zigzag level order traversal of its nodes values. From left to right, then right to left for the next level and alternate between. What? 3? I'm not sure. Zigzag level order traversal of its nose values. Ah, I see. So for first level, left to right. For second level, right to left. For third level, left to right. That's all. It feels like easier than previous one. Okay. Let me do it quickly. Oh, 3 node. And my PC get slow. Maybe I have better restart it. Zigzag level order. The number of nodes, not too much. Not too much. Oh. How about use BFS? Cause BFS would be the best solution because I don't know. Python Q. Put priority queue, not priority. First in, first out. Q. Yeah, this is what I want. And we declare the answer M. Yep. Node and depths. Get or pop. Get. Remove and return item from the queue. Yeah, that's it. Node depths. And append the node bar, right? Renew the current answer array. Oh wait, append current answer, right? Depths, and after that, node left and node right. Oh, maybe we don't need to use. We don't need to use Q because oh wait. Tips one. Live depth. What what I want to do is control the order because it's Q, so let me think about it. Ah. Put the 5 and we can append 2 and 6 at the same time, and we get 6. So when we get 6, and let's assume that it have children left and right, and 2 is also left and right. In this case, append from right or left or right or left, and then when we after process 2, we can get from this, okay, because it's stuck. Pum 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 pum. Fun fun fun. Yeah. So node right. Okay. reverse when it turns to reversed. Depth is same as we just append, but the depth is changed. Depth is updated. Reversed is true. Not depth reversed. Append the current answer and renew the current answer and update the previous depth. Depth is incremented and change the flow, change the direction. When it is reversed, we append the right to left, right to left, right to left. Okay, and we get the same depth element, so we just append the node value to the current answer. Okay, and we can update the queue if it has children. Yeah, should append the queue to the queue. Okay, to right, left, to right. I think this might work. Non-type. Depth 1, 2, 2 2. What is it? Oh, I see. Huh? Oh. Oh. Hmm? Current answer. It's pop it. Okay. So the depth is this. Depth start with 1, so we can append root node here, and really? Why? 9. 3 depth 1 and 9 depth 2 and 20 depth 2. 920. 715. Totally wrong. I was wrong. Yeah. How? We should prepare hash map and using depth as a key for the key. Yeah. Okay, I was wrong. linked list. Okay, and card depth. Okay, and hash map 0 would be root. Okay, and we can get card depth. Okay, and depth car. Values is like this, and values append and val, right? And val, right? And if is reversed, right to left, go right to left. So hash map current depth plus 1 append node right if node right. Okay, not node and left. Else hash map car. I think we don't need to use hash map. We just we have just two arrays to store the nodes, because yeah, you can see current depth and current depth plus 1 are needed for this code, so we don't We don't have to use hash map, but it's okay. And after loop, like this. Let me see the memory limit exceeded. Really? Really? Memory limit exceeded. If it's reversed, row 2 is used, so we can use row 1. Okay. And the next is reversed. Really? Why? Three, 9, 27. Huh? Why this is not good? The first one is not good. True. Really? Three, 2, 4, 5. Really? Hmm? Three. Wait, no, why? Three. Hmm. Three. Oh. Oh yeah, oh yeah, oh yeah. So 3, 2, 4, 5. Oh. Sorry. Have to pop. Okay. Yeah, this is what I wanted to do. Let's go. Okay, thank you. I have to explain this code. Yeah, first we handle edge cases. Handle the edge case. Okay, and we have to prepare two arrays to store the node in the same depths at the same depths. First in the base case, and the other one is used to store the nodes at the next steps. Okay, and flag to use, switch the array to use, basically continue flag. This is used to break the while loop. Yeah. It turns true when they are at the next steps. Okay. Because first in, last out. Okay. And we append a node at the next steps. opposite order. Okay. Which is opposite order. Left to right, left to right, right to left, left to right, right to left. Yeah. Like this. My PC is slow. It's annoying. Some singular plural mismatches, okay. Overuse of the node and theory, just to know that. Sound mechanical, like this is used to predict. Grammatics. First, hand the edge case. We'll use two lists to store nodes by depth. Base case start with a root and used for the next level. Flag to track the zigzag direction, and if there are no more nodes for the next level, we'll break later. Choose which row. Choose which row we are currently processing. We use a stack-like structure. Last in, first out to get a zigzag pattern. Pop the node from the end. Add its children to the other row in the current order. If there are still nodes to process in the next level, flip the zigzag direction. Reset the list for the next level. Okay. Sounds more natural in spoken code explanation. Yeah. First handle the simple edge case, and we'll keep two lists to store nodes at alternating levels. This is our starting point, level 0. We will use this one. We will use this one for the next level. This flag helps us switch direction each level. This flag will tell us if there are more nodes to process. We'll process nodes from one of the two rows depending on direction. We are treating the list like a stack here, since popping from the end works well for zigzag traversal. Okay, I got tired. Let's finish. Thank you for watching.